Welcome back, everyone. Ready to dive into some more fascinating topics. Today, we're looking into fractal generation,
Oh, yeah.
specifically those mesmerizing deep zoom images you see
Right.
of sets like the Mandelbrot set.
Absolutely.
I mean, they're incredible.
Yeah.
You've sent over some really in-depth articles on this. So
Yeah, I actually do.
let's unpack them.
Sounds good.
Yeah.
So, you start with this really simple equation. Z goes to z squared plus c,
Okay.
and you just iterate it over and over and over again. And depending on that initial value of c,
Yeah.
the results either explode off to infinity or they stay bounded.
Right.
And the Mandelbrot set is just all those c values that stay bounded.
It's interesting.
And visually, it's infinitely complex.
Yeah.
But the math behind it is actually pretty elegant.
Yeah, it really is.
Yeah.
It's amazing how much complexity can come from such a simple place to begin.
Mm.
But generating those deep zoom images,
Right.
I mean, those detailed views deep inside the Mandelbrot set, that's where the challenge lies, right?
Absolutely. As you zoom deeper and deeper, you're basically looking at smaller and smaller differences in those C values.
Yeah.
And that requires crazy high precision, way beyond what standard computer numbers can handle.
Right.
And it also means performing more and more iterations of that equation for each pixel on the screen.
Right.
So computationally, it gets really intense, really fast.
Yeah, so how do we get around this computational bottleneck, I guess you could call it?
Yeah.
You mentioned perturbation theory rescaling and series approximation. These sound like they're clever shortcuts.
Yeah, they are. Each one kind of targets a different aspect of that computational challenge.
Okay.
So let's start with perturbation theory.
Okay.
Instead of calculating the full high-precision result for every single pixel,
Right.
we can take advantage of the fact that the Mandelbrot set's equation is continuous.
Okay.
So small changes in the input C value lead to proportionally small changes in the output, at least initially.
So instead of brute force for every pixel, is there some kind of reference point we can use?
Exactly. So you choose a high-precision reference point, calculate its orbit through all those iterations, and then calculate these low-precision differences, we call them perturbations, for the nearby pixels.
Okay.
So you're essentially approximating their orbits based on how they deviate from that known, highly accurate reference point.
So we've got a reference orbit and these perturbed orbits around it.
Right.
Does that actually save a lot of computation?
It does, because you're only calculating these small differences instead of the full values.
Right.
You can get away with using lower precision for a big chunk of the image.
Okay.
And that significantly cuts down the computational load.
Okay.
And lets you zoom in way deeper into the fractal.
That's really clever.
Yeah.
But I imagine, like any approximation, there's some downsides to this. Your notes mention perturbation glitches.
Right.
What are those?
So glitches show up as like noisy areas or weird visual artifacts in the deep zoom image. Okay.
They happen when that assumption of like continuous gradual change breaks down.
Gotcha.
There's a researcher named Mandelbrot who developed this method for detecting these glitches.
Okay.
It uses an inequality that compares the magnitudes of the reference point and the perturbed points.
Okay.
And if the magnitude of that perturbed point plus the reference point is much smaller than the magnitude of just the reference point, that's a sign that there might be a glitch there.
So we have a way to find them, but what about fixing them? Do we just have to scrap perturbation in those areas completely?
Not necessarily. You can add more reference points to increase the accuracy in those problem regions, or you can rebase the calculations to a new reference point that's closer to the glitch.
Okay.
It's kind of like zooming in further, but with a shifted center point.
Okay, so perturbation is a way to work smarter, not harder.
Right.
By using these reference points.
Exactly.
And I imagine this is a big part of why we can generate these super high-resolution images of the Mandelbrot set we see today.
So what about rescaling? What role does that play?
So rescaling tackles another fundamental challenge,
Okay.
which is the limits of how computers actually represent numbers. So as you zoom deeper and deeper, the numbers you're working with, those tiny, tiny differences in C values, they get so small that eventually you hit a wall with what standard double precision numbers can even represent.
Okay.
And that's called underflow.
Underflow.
And it can lead to inaccurate results.
So even if we have clever algorithms, we're still limited by the tools.
Yeah, exactly.
How do we work around this underflow problem?
So early solutions involve techniques like floatex,
Okay.
where you store the mantissa and exponent of a number separately.
Okay.
That allows you to represent a wider range of values.
Okay.
It worked,
yeah,
but it was computationally pretty expensive.
So it solved one problem but created another one.
Right.
Is there something that's more efficient?
Yeah. So then came this method called unevaluated product, which cleverly rescales the values during the calculations to keep them near 1.
Okay.
So you're avoiding those super tiny numbers that cause the underflow. Right. It's like you're zooming in on the calculations themselves to prevent those tiny values from slipping through the cracks.
That sounds much more elegant than having to handle everything in software with separate mantissas and exponents.
Right.
Does this rescaling happen continuously or only at certain points during the calculations?
So it happens periodically throughout the process.
Okay.
And there are even some optimizations where you can actually skip certain calculations when the scale factors themselves underflow.
Right.
Because their impact would be tiny anyway.
So we've talked about perturbation theory for efficient pixel calculations.
Right.
And rescaling to kind of deal with this number underflow issue.
Exactly.
What challenges are left even with all this?
Even with rescaling, you can still run into situations where the reference point itself underflows, and that's where full iterations come in. So you have to resort to full-range, high-precision calculations.
Okay.
Often using that floatex technique we talked about.
Yeah.
But only strategically at specific points to avoid unnecessary computation.
It's all about finding a balance.
Yeah.
This has been so insightful.
Sure.
So far, we've gone from this basic concept of the Mandelbrot set to like the intricacies of perturbation theory and this clever rescaling.
Yeah.
What other techniques are really important for generating these deep zoom pictures?
Well, we've only just scratched the surface.
Okay.
Let's move on to the world of hybrid fractals.
Okay.
And a technique called series approximation, which can speed up rendering even more.
Okay.
You ready for that?
Let's do it. Hybrid fractals sound intriguing.
Yeah.
What makes a fractal hybrid?
So think of it like combining visual elements from different fractals.
Okay.
You know, you could take the spiral patterns of the Mandelbrot set and blend those with the intricate rigging you see in the burning ship fractal.
Okay.
So hybrid fractals let you create new and unique forms by mixing and matching these different formulas.
So we're not sticking to one formula, but kind of interleaving them.
Yeah, exactly.
Creating these hybrid iteration sequences.
Right.
That sounds like it adds a whole new level of complexity.
It does.
How do techniques like perturbation, which rely on that continuous change, how do they work with these hybrid formulas?
It's actually surprisingly systematic.
Okay.
So you break down that hybrid formula into its individual operators.
Okay.
Then you apply perturbation to each one separately.
Gotcha.
And then you combine those results.
Okay.
It's kind of like a modular approach.
Yeah.
You treat each piece independently.
So we're perturbing each piece of the formula and then reassembling it in its perturbed form.
Exactly.
Okay, that's really interesting. How about rescaling with these hybrid iterations?
Yeah.
I imagine that gets even trickier.
It does require some careful handling.
Yeah.
But the core idea is the same. If the reference orbit's values get too small, you got to switch to those full range iterations to prevent that underflow.
Okay.
Otherwise, you just very carefully propagate that scaling factor through all the calculations to keep everything in a manageable range.
It seems like breaking these complex problems down into these smaller, more manageable pieces.
Yeah.
It's a recurring theme here.
It is. That modularity is key to dealing with all that complexity.
Yeah. Okay, let's switch gears and talk about series approximation.
Okay.
This technique, I understand, lets us kind of skip ahead in the iterations.
Exactly.
Saving a bunch of computation. How does that work?
It takes advantage of the fact that if you keep iterating that perturbation formula, you actually end up with this polynomial series. And it depends on that starting C value. So you calculate that series once for a given reference point.
Okay.
And then to approximate the result of like tons of iterations for those nearby pixels. You just plug their C values into this pre-calculated series. It's like you're fast-forwarding through the process.
So instead of doing every single iteration step by step, we use this series to just jump ahead.
Exactly.
And get a good approximation. That's brilliant. But how do we know when it's safe to use this approximation?
Yeah, good question. So there are techniques you can use, like using probe points. Where you basically compare the series approximation with the full calculation at a few specific points. And if the approximation starts to drift too far away, It's time to switch back to that regular iterative method.
So it's about balancing the speed and the accuracy.
Exactly.
Using the approximation when it's reliable, but going back to the full calculation when needed.
Right.
You mentioned bi-series approximation too.
Oh, yeah.
Is that an extension of this idea?
It is, but it's even more powerful.
Okay.
So bi-series approximation exploits this special property of periodic points in fractals.
Okay.
Some points, when you iterate them, they eventually fall into this repeating cycle. And bi-series approximation lets you skip entire periods of those cycles.
Wow.
So you get even bigger speed-ups than regular series approximation.
So we're not just skipping like a few iterations.
No.
But whole repeating sequences.
Exactly.
I imagine that's especially useful in those really detailed areas of the fractal, where you have all those repeating patterns.
Exactly. And while it's super effective, it's harder to apply to fractals with absolute values or those hybrid formulas we talked about.
Okay.
So that's an active area of research.
It seems like there's always a new challenge to tackle.
Sure is.
Pushing the boundaries of what we can do.
Yeah.
All these techniques we've discussed, perturbation, rescaling, series approximation, they've completely changed how we create these detailed fractal images.
They have. And it's an ongoing evolution.
Yeah.
We're still finding new ways to improve efficiency and accuracy.
Yeah.
And to delve deeper into these infinite structures.
It's amazing how much thought has gone into making these images possible.
It is.
What are some of the areas of research you're most excited about now?
There's a lot of promising avenues.
Yes.
One that's getting a lot of attention is optimizing the rendering of those deep needle regions.
Okay.
Remember, those are the areas that still need those really expensive full-range calculations.
Right. So even with our fancy algorithms, there are still some regions that are holding on to their secrets.
Exactly.
What other challenges are researchers looking at?
Well, exploring even more advanced forms of series approximation is a hot topic.
Okay.
There's chained bi-series approximation.
Okay.
Which uses sequences of those smaller repeating structures, the mini-brots,
Right.
to skip even larger chunks of iterations.
So it's like we're using those self-similar structures as stepping stones to navigate the fractal.
Exactly.
That's a fascinating idea.
Yeah.
So where does all this leave us? What's the takeaway from all these techniques in this research?
I think it really highlights how, even in a field like fractals, which can seem so abstract, there's this constant push to see what's computationally possible.
Right.
It's this interplay between the math theory, the algorithm design, and the artistic side of it that makes it so captivating.
It really shows what happens when those different areas come together.
Yeah.
And it shows that even with all our technology, there's still so much more to learn.
Absolutely.
New challenges to figure out.
The world of fractals is a constant reminder that learning and understanding never really ends.
Yeah, it sounds like the future fractal generation has so much potential.
It really does. And it's not just about making the resolution better or the speed faster, you know.
Right.
Researchers are looking for new ways to use these techniques.
Okay.
For example, fractal patterns are being used in antenna design.
Interesting.
Their unique properties can lead to antennas that are smaller and more efficient.
That's a perfect example of something that starts out as just math exploration and ends up with real-world uses.
Exactly.
We've talked about a lot in this deep dive. We've seen how these different methods like perturbation theory, rescaling, and series approximation have changed the game for creating pictures of fractals. But I think what's really amazing is how much ingenuity is behind it all.
Yeah.
It's a testament to human creativity.
Absolutely.
And our desire to understand and visualize the beauty of mathematics.
I couldn't agree more. And what's even more impressive is that this field is still pretty young.
Yeah.
We've only just begun to explore what's possible with fractal generation.
Right.
Who knows what we'll discover and how we'll use it in the years to come.
That's what makes this topic so fascinating. There's always more to learn, more to explore, and more to create.
Yeah.
So if anyone listening has been inspired by this deep dive, I encourage you to check out some of the incredible fractal generation software that's available.
It's really cool stuff.
Experiment with it. Play around with different formulas and techniques and see what you can create.
Might even discover something new.
And if you're feeling really adventurous, dive into the math behind it.
Oh, yeah.
There are lots of great resources online and in libraries that can guide you through the amazing world of fractal geometry.
Definitely.
It could be surprisingly accessible and rewarding.
Absolutely.
It's been great exploring this topic with you.
Likewise.
Thanks for sharing your knowledge and insights.
My pleasure. Thanks for having me.
And to our listeners, thank you for joining us on this deep dive into the world of fractal generation. We hope you found it as fascinating as we did.